All right, these notes are going to go into your HBS comp book, but I wanted to show you first before I get into it. I use these little post-it notes for each one of my organ systems. So I got skeletal system, muscular system, respiratory system. That way I can easily go right directly to that organ system in my notes. So I've got the name of the organ system on one side, and then on the other side I have the functions of that organ system. So the functions of the skeletal system are support and protection, movement, mineral storage, and to make blood cells. So if you don't want to use the post-its, that's fine, but make sure that you have those functions of each organ system written down somewhere. We have talked about a few of these different types of images and tools to scan parts of the body, but we're going to be a little bit more specific about them right here. So an X-ray uses electromagnetic radiation to produce images of internal tissue, bones, and organs. So the key for the X-ray, electromagnetic radiation. The X-ray passes through, you're not going to get an image. So X-ray passes through equals no image. The X-ray is absorbed, then you get an image. The calcium in our bones absorbs X-rays, and so that's why you see an image of our bones when an X-ray is taken. Next is CT scan. CT scan is a computerized tomography scan, and basically what it's doing is it's taking and combining a bunch of different X-rays from different angles so that you get a more detailed picture. So it's similar to an X-ray, but you have a much higher level of detail, and you have 360-degree view, so you can see all around. We have already talked about MRIs. MRI is a magnetic resonance imaging. This is a diagnostic test to image the body, and it can show bones and soft tissue, blood vessels, and other kinds of things rather than just bones. An ultrasound. An ultrasound gives you images of internal structures and organs because the ultrasound pulses echo off the tissues with different reflective properties. And so because they're coming back at you with different reflective properties, that's what's giving you that image. So basically it's sending out pulses, and they echo off those tissues, and that's where you're getting your pictures. The ultrasound is the tool that can capture motion. So you can be taking an ultrasound of your heart as it's beating, or as tissues and muscles as you're breathing. And ultrasounds are often used to see the unborn baby and see how they're developing, and you can see movement at that point. So it's really helpful in that way. All right, so skeletal system. We talked about cellular organization. So within the skeletal system, cellular organization, similar cells build tissue, different types of tissue create an organ, different organs create the whole organ system. In this situation, the cells of the skeletal system are called osteocytes. The tissue could be spongy bone or compact bone. An organ, an example of an organ of the skeletal system is the humerus, and that's the bone in your upper arm. So bones are organs. They're not dead material. They're actually living material. And of course, the organ system is the skeletal system. All right, different types of bones. One type of bone is called a flat bone. Flat bones are thin plates or sheets. They protect internal organs. So when we say flat, they're not completely flat. They're usually just thinner plates or thinner sheets. So flat bones protect our brain, they protect our heart, they protect our pelvic organs, because some examples of flat bones are the skull. So the skull is a very thin kind of plate, and it protects our brain. Sternum protects our heart, ribs protect our heart, ilium, ischium, those are protecting our pelvic organs. So flat bones are thin plates or sheets. They protect internal organs like our brain, heart, and pelvic organs. Some examples of flat bones are the skull, sternum, ribs, ilium, and ischium. Long bones, they support your body weight and allow for movement. Long bones support your body weight and allow for movement. Some examples of long bones are the humerus, radius, ulna, femur, phalanges. So femur, humerus, even radius and ulna, those bones in the arms and the legs are probably more along the lines of what you think of when you think of a bone. Phalanges in your hands or feet, those are also very similar in shape, and they're not as long, but they're similar in shape as these other bones, and function for sure. All right, short bones. Short bones are boxy / cube-shaped bones that provide stability. Short bones are boxy / cube-shaped bones that provide stability. For example, the tarsals in your ankle, the carpals in your wrist, they're boxy, cube-shaped, and they definitely provide stability for your wrist or your ankle. Then finally, we have irregular bones. They're going to vary in size and shape and structure, or they have a complex shape. So irregular bones vary in shape, size, and structure, so they're different. They don't fit in any one of the other categories. They themselves are going to have a lot of variety. Or those irregular bones, they have a complex shape. Some examples of irregular bones are our vertebrae and our sacrum. All right, so next, you'll have a picture that looks like this, and underneath here we're identifying almost all of these numbered structures that are on this bone. So on this long bone, we're taking a look at all of these structures. So first, I've got number 1 and number 3. Number 1 is a proximal epiphysis. Number 3 is distal epiphysis. So proximal, closer to the point of attachment, closer to the median of the body, distal, further away. So when we look at this bone, which looks like the humerus, this is the proximal epiphysis. This is the distal epiphysis. So this region right here and that region right there. The epiphysis is just a word that means the end of a long bone. All right, number 7, this section right here is the diaphysis. Diaphysis is kind of like the body or the shaft of a long bone. So number 7 is the diaphysis, is the body of the long bone. All right, number 11 is pointing to this area right here, and number 11 is the growth plate or epiphyseal line. It is also known as metaphysis, where the epiphysis and the diaphysis come together. So this is the growth plate, the epiphyseal line, also known as, aka, the metaphysis, where the epiphysis and the diaphysis meet. So number 11 is our growth plate. All right, next we have number 5 and number 10. So 5 is this part right here, the white part. 10 is the white part right here, and that's cartilage. Cartilage holds bone together. It protects. It helps with movement / cushions joints, and it also helps to absorb shock. So number 5 and number 10, the kind of white parts on that picture, that's cartilage. It holds bone together, protects, it is important with movement / cushioning joints when the bones move, and it helps to absorb shock. All right, number 9 is pointing to this part right here, which is like empty space, which is space, not necessarily empty space, but it's space right here in the middle of the bone. And number 9 is the medullary cavity. The medullary cavity is the location of yellow marrow. Medullary cavity is the location of yellow marrow. Number 2 is kind of pointing right here, but it really indicates the thin tissue that's across the top of the bone because it's the periosteum. The periosteum is the membrane to protect the bone. It covers the bone. So number 2 is indicating the periosteum, which is a membrane that covers the bone, that covers the bone to protect the bone. All right, number 8, we have here. Oops. Okay, so 8 is looking at this part right here, which is the spongy bone. So 8 has spongy bone right here, and then it says compact bone, but compact bone really doesn't have a good label on here. This part right here would be our compact bone. This right here would be the spongy bone, and you're going to do an activity where you can tell the difference between them. So number 8 is pointing to this part right here, and that's the compact bone. Or I'm sorry, number 8 is pointing to the spongy bone. Compact bone would probably be a little bit if we had something that was labeled right here, but we don't really have anything that's got a good arrow to that. All right. So when we did our levels of organization, we talked about the cells being the building blocks, and that's where we start. And so the cells in the skeletal system are called osteocytes. Osteocytes are bone cells. There are two types of osteocytes, an osteoblast and an osteoclast. Osteoblast builds up bone. It takes the calcium from the blood and stores the calcium in the bone, and so in doing so, it builds up more bone tissue, more bone. Osteoclast breaks down the bone to release calcium into the blood. Osteoclast breaks down bone, and when it breaks down bone, it releases that calcium that's stored in the bone, it releases it back into the blood. And so just an interesting term here, you're kind of always looking at words, but hyperplasia, hyper, means more, increased, high. Plasia has to do with formation, especially when we're talking about cell formation. So whenever we see hyperplasia, we know that that's a sort of disorder that we are having too many cells that are being formed. And some kinds of blood cancers or blood diseases and disorders can create hyperplasia within bones. Okay, so that labels the picture. Next, we're going to look at spongy bone and compact bone. So I have divided up my pages, so I've got spongy bone information and compact bone information. All right, spongy bone, structure of the spongy bone. There are lattice-like matrix of thin columns or plates of bone called trabeculae. And so I had to spell that out for myself, or put that out for myself. Trabeculae. Lattice-like matrix of thin columns or plates of bone called trabeculae. Spongy bone is very porous. It has lots of vascular tissue. Remember, vascular tissue means blood vessels. Lacunae, cavities for osteocytes. So they have lacunae, which are cavities for osteocytes. And that makes it very porous, that whole makeup right there. All right, so here's the picture, and notice how it's oriented, because this represents red bone marrow, and this represents yellow bone marrow. And so I've used red and yellow crayons to help myself out with that a little bit more. All right, so red bone marrow is found in flat bones, like in the hips, sternum, the ribs. Red marrow is found in the epiphyseal ends of long bones. Red marrow is found in flat bones, like the hips, bones of the hips, the sternum, and the ribs. Red marrow is found in the epiphyseal ends of long bones. Red marrow contains hematopoietic stem cells. Red marrow contains hematopoietic stem cells. And these cells, stem cells, can basically be differentiated into all sorts of different kinds of cells. They can go on to develop into lots of different things. The hematopoietic stem cells are going to turn into one of three things. They're going to turn into erythrocytes, red blood cells, leukocytes, white blood cells, or thrombocytes, which are platelets. So our blood cells, red blood cells, white blood cells, and platelets, our blood cells, come from bones, and specifically the red marrow in the bones, because that's where they have the hematopoietic stem cells. Erythropoiesis is the production of erythrocytes. So that's just the process. Erythropoiesis is the production of erythrocytes. All right, yellow marrow. Yellow marrow is found in the medullary cavity of long bones. So yellow marrow is found in the medullary cavity of long bones. Yellow marrow contains mesenchymal stem cells. Red marrow, hematopoietic stem cells. Yellow marrow, mesenchymal stem cells. So once again, we have cells that can turn into basically different kinds of things. So some of them are going to develop into turn into fat cells. Some are going to develop and turn into cartilage. Some of them are going to develop and turn into bone cells. All right, compact bone. Structure of compact bone is a matrix of mineral salts like calcium and phosphorus and protein fibers like collagen. Compact bone is a matrix of mineral salts like calcium and phosphorus and protein fibers like collagen. So the mineral salts allow bones to withstand compression pressures, so the squeezing pressure. So that's what makes it strong against squeezing or compression pressure. Mineral salts allow bones to withstand squeezing/compression pressures. The collagen fibers, they have great tensile strength, so it allows bones to endure stretching. So this endures the squeezing pressure, this endures the pulling pressure. So collagen fibers have great tensile strength, so bones can endure stretching. So those characteristics are what make bones so strong. All right, so the lacunae, these are tiny spaces for osteocytes. Spongy bone has lots of lacunae, lots of cavities for osteocytes. When we look at the structure of a compact bone, things are just a little bit different because once again, it's compact. It doesn't have a whole lot of space. So here's my picture right here. And then underneath I've got it labeled the number 1, yellow, blue, and green on here. So this is number 1, this is the yellow, this is the blue, and this is the green. So that's my label on here. All right, so osteon and osteon, they are cylinders, and they are considered the functional unit of compact bone. And I've labeled that number 1. So osteon, they're cylinders, cylindrical, functional units of compact bone. So this right here, this represents an osteon. Osteocytes are the bone cells. Osteocytes are the bone cells, and they're highlighted yellow, so each one of these little specks right here, those represent osteocytes. I highlighted them yellow. Next, in blue, is the Haversian canal. The Haversian canal is where blood vessels and nerves run through. So I've highlighted it blue, and then the space in between would represent the Haversian canal. So here's our Haversian canal, the space where blood vessels and nerves run through. And then finally, canaliculi. So canaliculi are the little green squiggles on here. So canaliculi are these little green squiggles. And there's more than that. There's more osteocytes than that. There's more canaliculi than that. But I'm just giving you an example. And so these are gap junctions. And these gap junctions allow the cells to be very close together. But then those gap junctions, those spaces, allow nutrients and small molecules to pass between osteocytes. So canaliculi are gap junctions that allow nutrients and small molecules to pass between osteocytes. Okay, one last thing. Feedback loop. Negative feedback loop, because it's kind of got a figure 8 look to it, and it's simplified. But it's simplified for what we need. So we always want to maintain homeostasis. We want to maintain that balance, but every once in a while, calcium levels go up. So you eat a meal, you eat a bunch of cheese, drink a whole bunch of milk, whatever. And then your digestive system breaks it down, dumps all that calcium in your bloodstream. Well, sensors in your body pick up the fact that there's an increase in calcium, and then they send that information to your brain, beep, boop, 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 that processes it and says, okay, well, we need to get that down. So it's going to stimulate your thyroid gland. Your thyroid gland is going to release a hormone called calcitonin. So the thyroid gland releases the hormone calcitonin. That hormone calcitonin is going to act on your bones and on your kidneys. Calcitonin acts on your bones and gets those osteoblasts going because the osteoblasts build bone. And so that calcitonin tells those osteoblasts to start building bone and pulling the calcium from your blood and putting it in the bone to store it. So thyroid gland releases calcitonin. Calcitonin acts on the bones. The osteoblasts become active, and there is calcium reabsorption. So the calcium gets stored in the bones. The calcitonin also acts on your kidneys, and it tells your kidneys, as it's filtering your urine and getting that stuff ready to be removed from the body, it tells the kidneys to stop holding on to so much calcium, reduce the uptake of calcium. So there's going to be more calcium out as a waste product. We're not going to put it back into our blood. Then eventually that's going to lead to our blood calcium levels dropping, but we're not constantly eating. And so eventually in between meals, our calcium levels are going to drop, but we constantly need calcium for muscle contraction and part of our nervous system. We'll find that out. But at any rate, we constantly need a supply of calcium. And so when our calcium levels drop, sensors in your body pick that up, take it to your brain, beep, boop, beep, boop, decides what to do with it, and your brain sends out a signal. Parathyroid gland is then going to release PTH, parathyroid hormone. So parathyroid gland releases a hormone, PTH, and PTH affects your kidneys, affects your bones, and affects your small intestines. PTH affects your kidneys, tells your kidneys to increase uptake. So don't get rid of excess calcium as a waste product. Put it back into the blood. PTH affects your bones, and it gets the osteoclasts working. Osteoclasts crush the bone. Osteoclasts break down bone. And so as they break down bone, they're going to release calcium, and calcium is going to be released back into your blood. Small intestines, they're going to increase uptake as well, so don't get rid of that calcium in the solid waste. Keep that, dump it back into your blood because we're still going to need that. All of those things working together is going to cause blood calcium levels to rise so that we can maintain homeostasis until they go up again.